All right, this is Tuesday, January 12th, 2021, Physics CP Example 1. We have 3-point charges in a row. The first charge, Q1, has a magnitude of 2.30 coulombs, and we'll say that's x equals 0. Then a distance of 2 meters to the right of it, charge Q2 has a value of 1.70 coulombs, another positive charge. 2 meters to the right of that, charge Q3 has a value of 3.40 coulombs. I'm going to calculate the net force on Q1, and then the net force on Q2, and then the net force on Q3, because the net force is going to be different for each one of these three charges. So you might as well be able to do it for any of them once you have this geometry set up. The equation that I'm going to be using is Coulomb's law. The force of electrical attraction is the product of Boltzmann's constant, lowercase k, times the magnitude of the first charge. I guess to be not confusing, I'll use subscripts A and B on the formula. So the first charge QA times the second charge QB divided by the distance between A and B squared. The charge has to be expressed in units of coulombs. The distance has to be expressed in units of meters for everything to work out correctly. So for example, if I said 5,000 protons, I would have to multiply those 5,000 protons by the charge on one proton to convert it to the number of coulombs expressed by 5,000 protons. Now this problem is already in units of coulombs and in meters, so there's no conversions needed for this one. The process is I'm going to start with Q1. I shut off all the other charges. I turn the other charges on one at a time, calculate the force of attraction or repulsion between them, shut that charge off, turn the next one on, calculate the force of attraction or repulsion, and go through the list. Now our list is only 3 charges total long, so it's kind of a short list. But if I had 20 charges, it'd be the same math process over and over and over. One more reminder, since opposite charges attract, if one is positive and the other is negative, then the minus sign in Coulomb's law means they attract. Like charges repel. So if I have a positive times a positive or negative times a negative, that's also a positive. That means a positive result is repelling each other. Okay, so here we go. The first charge I will do as the force between charge 1 and charge 2. Into Coulomb's law, I'm going to plug in K. For Q1, it's going to be 2.3 coulombs. For Q2, it's going to be 1.7 coulombs. The distance between charge Q1 and charge Q2 is 2 meters. So I'm going to divide everything by 2 meters squared. Powering up my calculator, it certainly is convenient to have Boltzmann's constant stored as K in my calculator. That means I only have to type alpha K on the TI, and then 2.3 times 1.7 divided by 2 squared, which you know in your head is already 4. And my calculator gives what looks like a big number that you can't quite see because I have my brightness so high. And that's, yikes, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 9.79 giganewtons. All right, 9.79 giganewtons, where giga means 10 to the 9th power. That's what a gigabyte is on your calculator memory. That is repulsive because they are both positive charges. And so that is pushing Q1 to the left. Next, I'm going to calculate the force of electrical attraction between charge Q1 and charge Q3. Well, that's going to be K times 2.3 coulombs times Q3 is 3.4 coulombs. The distance between them is 2 meters plus 2 meters is 4 meters. Plugging that into my calculator, since they're both positive charges, it's going to be repulsive. Alpha K 2.3, oops, mistyped it, 2.3 times 3.4 divided by 4 squared. This result is 4.39 giganewtons of repulsion. Okay, there it is on the calculator. Now, to calculate the net force on charge 1, and by the way, there's only one other calculation I need to bother doing. If you like, I will do that one next. I'll go ahead and calculate what is the force between charge Q2 and charge Q3. They're both positive, so they're going to repel each other. It's going to be the product of, I guess I'll write it out, K times 1.7 coulombs times 3.4 coulombs divided by 2 meters squared. All right, well, calculator says alpha K times 1.7 times 3.4 divided by 2 squared. Holy kashmoli, I get positive 13.0 giganewtons. It's so fine my calculator switched to scientific notation. It displayed 1.299055 times 10 to the 10th power, which I know is 12.99 times 10 to the 9th power, and the 3 sig figs, that goes up to 13.0 giganewtons. Now that I have these 3 calculations, I look at my geometry to interpret what to do with those values. Each one of the 3 is positive. Each one of the 3 means they're pushing each other apart. Q1 is pushing Q2. Q2 is pushing Q3. Q1 is pushing Q3. Everyone is pushing against everyone else. So for Q1, I've got 9.79 giganewtons pushing Q1 to the left from Q2. In addition to that, I have 4.39 giganewtons pushing Q1 to the left as well. So the net force on Q1 is the sum of 9.79 plus 4.39 in units of giganewtons. So I'll even write them in giganewtons. 14.2 giganewtons pushing it to the left. That is the net force on Q1. The net force on Q2, so now you have to look at the geometry more carefully. Q1 is pushing Q2 to the right with a value, let me do a little sketch, I guess, pushing it to the right with a value of 9.79 giganewtons. Q3 is pushing Q2 to the left with a value of 13.0 giganewtons. So in this geometry, I don't add the 2 numbers together because they are in opposite directions. I have to subtract the numbers from each other. 13 minus 9.79. and I end up with 3.21 giganewtons pushing Q2. Now, which one is stronger? The one pushing to the right? The one pushing to the left? It's the one pushing to the left. So I would say the net force is 3.21 giganewtons to the left. Now I do exactly the same process for Q3. For Q3, I have Q1 pushing Q3 to the right. So I'm going to be calculating F net on Q3 is equal to, if I do a little sketch, I got Q1 pushing Q3 to the right with a value of 4.39 giganewtons. I have Q2 pushing Q3 to the right with a value of 13.0 giganewtons. These are both pushing Q3 to the right. So these two forces add together. In this case, I go 13 plus 4.39, and it says 17.39. Strictly speaking, I can only go to the nearest tenth. So 17.4 giganewtons, and both of these are pushing it to the right. Ta-da! For this example, I have calculated the net force on Q1, the net force on Q2, the net force on Q3. They are all different based on the actual geometry and values of the problems.